Okay. Okay. So let's get started. Has the TA announced the last final project? Oh, okay. So I think the TA will announce like the score for the first project as well as like the information of the final project shortly. Okay, maybe today or latest tomorrow. Okay, and the second project, as I mentioned, that we will extend it to like next week. Okay, because due to the field day, okay, so the class got canceled, so we can we can only cover enough content for the CNN, today, okay, and hopefully like they'll be good enough for you for the project 2, okay. And the project 3 will also be announced like later, maybe before next lecture, but do not worry, okay, because the third project is about like the prediction, okay, and the deadline is going to be set like at least after we cover the RNN chapter, okay, which is the chapter after the CNN, okay. So back to our class, okay. So last time, okay, actually 2 weeks ago, okay, we talked about the convolutional layer in CNN, okay. As I said, there are two important building blocks of CNN. One is convolutional layer. The second one is the pooling layer. Okay, the pooling layer concept is kind of similar to convolutional layer. So once you understand convolutional layer, it shouldn't be difficult to understand pooling layer. And to be honest, the pooling layer has a much easier function than the convolutional layer. Okay, remember convolutional layer has like the kernel size, the stride, everything, right? The pooling layer also has those. Oh, okay. Yeah, the pooling layer also has all those components, okay, the elements, but it doesn't have the, remember like in convolutional layer, for each kernel, okay, for example, for a 3x3 kernel, okay, or a filter, okay, we need to have weights, right? And those weights, as I told you earlier, okay, are learnable, okay, they will get their values, okay, during training, okay. But the in pooling layer, okay, because its primary function is to subsample the input image, okay. When I say subsample, normally I mean shrink, okay, make it smaller, okay. So so really, like for example, say if you have a kernel size of maybe 3x3, then there are only two types of pooling layers. Okay, the first one is called Maxpooling. Okay, Maxpooling basically, because remember like those kernel or filter, okay, when, I mean, the way to get the value is like, you know, you use that filter to cover a small area, and then, you know, do some computation over the image in that small area, right? But for the pooling layer, if it's max pooling, then basically, okay, it just get the max value from those small area and output it. So it doesn't have any weight, okay, associated with the max pooling layer, okay, the kernel in the max pooling layer, okay. As for like the other type is called average pooling layer, okay, just by the name, it's obviously to you, like basically you just get the, you know, the average from the values in the area that is covered by this filter, okay. So the concept is very, very simple, and each time, okay, obviously this kernel, okay, or filter, okay, I mean, for each covered area, it only output one value, either the max value from this region or the average value from this region, but basically just one. Okay, so obviously it's you can imagine this is like we are doing subsampling. 这里快没电，你有电池吗？不是这个，这个我记得也有电池，可以帮忙。
那个
你们不是有买？对啊，实验室应该有这个东西。Yeah. Okay. So you may ask, so what is the purpose of this subsampling? Okay. The first important reason to do subsampling is to reduce the computation load. Okay, obviously, I mean, if you always need to handle, you know, this many pixels from the input image, okay, then remember we just mentioned about the memory consumption. You know, in the previous, yeah, we talked about this one, right? Like memory requirements for the convolutional layer. So, you know, if you always need to, you know, have this such a large size of image, okay, to deal with, okay, so it will take a lot of computational cost, okay. So this subsampling basically allows you to reduce the memory to a smaller size, which obviously, you know, help you to reduce the computational cost. On the other hand, okay, once you reduce the size of your image, okay, at the same time, the number of parameters also gets reduced, right? I mean, you know, not only the memory usage and the number of parameters also reduce, okay, because the image size gets reduced. I mean, every the parameter associated with the image size also gets reduced, which actually help you to, you know, avoid overfitting. Okay, the reason for the overfitting is because you have too many parameters, right? Okay, but now once you are able to reduce number of parameters, then you are able to sort of like you know, ensure you avoid overfitting. Okay, of course, I mean, if you still get overfitting, we still have all sort of techniques that we talked about in the last chapter to fight with the overfitting. Remember? Okay. So anyway, so that's yeah. Here, I mean, I just want to show you an example. For example, here, this is an example of max pooling. So every time, okay, this is a max pooling with a kernel size 2 by 2 and with the stride of 2. Okay, so every time we move 2 units to each dimension. But you can see, I mean, when we cover this area, we just, you know, obtain the largest value from this area and copy it to here. Okay, that's about it. Okay, that's it. Okay, that's what we meant by Maxpooling. And you can see that if this is the original image, okay, then the Maxpooling sort of reduce this image to this size. Okay, obviously by looking at this example, you can see we are doing the height and the height and the width both get reduced by half, right? And well, although you may think, okay, just getting the max value from each area doesn't, how should I say, like it doesn't do anything, but you can see that this smaller image actually maintain the feature of the original one pretty well, right? It just looks like the mini version of the original image, right? I mean, if you use the average pooling, it will also give you something, the effect that it's going to be similar. It's going to be similar. Okay, so another advantage, okay, for the Maxpooling is that, okay, it introduces the what we call invariance, okay, especially to the small translation, okay. Remember, like, what is you may ask, what is the invariance? Remember when earlier we talked about like for convolutional neural network, okay, if you learn a feature at one position, okay, you are able to be able to recognize that feature at any location of the image, right? That's the basic idea of invariance. But this is not this invariance property is unfortunately not available in the multi-layer perceptron. Okay, one example that I can show you, okay, is that here. This is we have a three. I mean, the lower three images obviously are three. Well, you can say it's number 8, right? Number 8. And what's the difference between these three images? This 8, okay, the whole 8 is moving 1 pixel to the right, right? And I mean, for this C, this 8 is moving another pixel to the right, basically. But so this is obviously, as I said, like a small translation, right? You guys understand what do you mean by translation, right? Translation in Chinese is 平移. Okay, I mean, I probably shouldn't use 平移. I should say like it could be, I mean, it could move any direction, but without changing the angle. That's called translation. Okay, so this, I mean, for these three, obviously we are moving horizontally. Okay, but the translation can also mean the the translation can also mean the vertical translation. Okay, so if we apply the Maxpooling of 2 by 2, okay, as I said, it's going to reduce the original image size, into 1/4, right? Because the height is reduced by half, and the width is reduced by half. So the total, obviously, the whole area gets reduced by, well, 75%, right? So, but the more interesting thing is that, okay, if you see, okay, when we apply the Maxpooling of 2 by 2, okay, this is the image that we are going to get. And for this 8, even though we move 1 pixel to the right, we are going to get the exact same thing here, right? And if we move more to the right, yeah, after the applying the Maxpooling of 2 by 2, yeah, the result change slightly, but still, like these 3 are very similar, right? Especially the first 2, they are identical, right? So this tells you that, okay, the Maxpooling is able to maintain, the invariance over small translations. Okay, in fact, okay, the same thing, okay, the invariance can be observed, okay, not only for translation, but also for, like a scale. Okay, if you change the scale a little bit, as long as it's not too big, okay, or if you change the, angle, okay, it also provide like a small amount of rotational invariance. Okay, so scale invariance, rotational invariance, and obviously, as I said, the translation invariance. So those are very important, because when you see something, if you recognize that thing, and you should be able to recognize the same thing if that thing, okay, move a little bit, or rotate a little bit, or like enlarge or shrink a little bit. I mean, basically it means the same thing, right? So this is like why the Maxpooling is a good. I mean, on the other hand, remember I told you there are 2 different pooling layers. The other one is average pooling. Average pooling does not maintain the invariance very well. I mean, compared with Maxpooling, okay, it doesn't provide the invariance, okay. The translation or rotational or scale invariance as good as Maxpooling. Okay. So this is the downside, okay, of the pooling layer. Okay. First, it is obviously very destructive, because basically like if you use just 2 by 2 pooling layer of stride of 2, the output will be 2 times smaller on both dimensions, which means like you lost a lot of information, right? You drop 75% of the input values. Okay, so this information, once it's gone, right? There's no, well, at least not an easy way to recover it. Okay, there are, sometimes we also talk about like how you can enlarge an image by CNN. Okay, we call that Subsampling. We'll talk about that later. Okay, at the end of this chapter. But that's a different issue. Okay, but anyway, the pooling, not only the Maxpooling, but also the average pooling. Okay, when you do this, you lose some information along this process. This is for sure, right? So another issue, okay, as I said, the invariance is is good for most of the recognition task, vision recognition task. Okay, if you want to do a class like object recognition or like a classification, okay, all these things. Okay, the invariance, obviously sounds like a good idea, but there are also other vision applications, okay, that the invariance is not necessarily a good idea. Okay, one example is semantic segmentation. Okay, what is semantic segmentation? Actually, using the words, okay, to describe semantic segmentation is not easy. Okay, let me just show you a picture. Okay, at the end of chapter, even though we won't talk about it, as I said, at the end of chapter. But once you see that image, you will have a very good understanding of semantic segmentation. Give me 1 sec. Yeah, we are going to talk about a lot of different applications. And yeah, this is fully connected layer. Okay, YOLO. Semantic, yeah, we are almost there. Yeah, here. So this is the original image. What semantic segmentation is that it is going to classify each pixel into the class where this pixel, belongs to. For example, all the pixels, that cover this person will be classified as people. And, these are the bicycle, obviously, okay? And we have the buildings, okay? And we have sidewalk, and this is motorcycle, okay? Well, bicycle too. Oh, I'm sorry. These are the bicycle, okay? And we have sky, obviously, and road, okay? And some more people, okay? So you can see that in this particular application, the small translation may not, may mean different object, right? Okay, so for example, like a pixel here, if you move one pixel to the right, it will represent a different object type, right? So in this type of application, okay, maybe the invariance, okay, translation invariance is no longer a good idea. Okay, so the Maxpooling may not, be very good. Okay, but again, this is application dependent. I have to say that for most of the vision tasks, okay, vision applications, we do prefer those invariant concept. Yeah, we will get to the semantic segmentation near the end of this chapter. Okay. Let me come back to. Okay. So how do we implement the pooling layer in Keras? It's very easy. Okay, you just provide a statement like this. Okay, just create a Maxpooling layer using the Keras.layers.maxpool2d. Okay, and obviously you have to provide the pool size, and usually this pool size also represent the stride, okay, the value of the stride, because eventually this is going to be used to shrink the image. Okay, of course, if it's not used for the first layer, then it's going to be used to shrink the feature maps. Okay. But basically, you get an idea. Okay, it is always its purpose is always subsampling. Okay, and if you want to create average pooling layer, okay, you just replace this maxpool2d by avg pool2d. That's it. Okay, so it's very easy. Okay, to add the pooling layer. Okay, and it will use by default valid padding. Okay, in other words, no padding at all, because normally we don't, when we shrink the image, we don't want to pad zeros, okay? So, okay, so far, the pooling that we are talk about, okay, we talk about for to pool like over the height and the width, the first two dimensions. But you know that, okay, when it comes to you know, feature maps, we have actually 3 dimensions, not only the width, the height, but also the depth, right? We a lot of time we have a lot of feature maps, right? And each feature map basically, you know, represent one particular feature, okay? And the pooling can also be done on the depth dimension. When I say depth dimension, I mean like you know, over, you know, different layers of the feature maps. Okay, so yeah, and you can sort of like what should I say, like expect the same thing will happen. Okay, because as I said, the pooling layer allows you to create invariance, right? So once you use the pooling layer over the depth dimension, then you also allow it to create invariance over different features. So what does that mean? Okay, let me give you an example. Okay, so in this example, for example, different features represent like different rotation angles. Then, you know, you sort of like if you use the pooling on the, you know, depths, then it allows you to create like a rotational invariance. This is much more stronger invariance. I mean, that you can create, you know, compared with like just using the Maxpooling over like a height and width dimension. So not only you can use it to create like you know, the rotational like you know, invariance. You can also use that to create invariance to anything else, such as thickness, brightness, skew, color, because they will be considered as different. I mean, they'll be considered in different feature maps, basically. Okay, so in order to create like an invariance over different features, okay, that's what I mean, we can pool over the depth dimension. Okay, and so how do we implement the depth-wise max pooling? Okay, unfortunately, Keras does not have a depth-wise max pooling layer. Okay, but TensorFlow has one. Okay, TensorFlow low-level deep learning API has one. Okay, so it's going to be something like this. So here, okay, this it's going to be 4 tuple. Okay, this k size is going to be 4 tuple. Okay, so this 4, okay, the first 3 values of this 4 tuple, okay, should be 1, because when we pool over the depth, okay, the height and the width should remain like just 1 unit. Okay, and this means the kernel size and the stride along the batch height and the width dimension. So it's the first is batch. Okay, the second one means height. The third one means the width. The last one, the fourth element in this 4 tuple means the depth. So that's why, okay, here, okay, is an example that we create max pooling over the depth. Okay, but the size is 3. Okay, padding, in this example, the padding is valid. Okay, and you need to make sure, okay, the number of feature map, okay, is divisible by 3. Otherwise, you run into trouble. Okay, so for example, if you have 20 feature map created in the previous layer, then you apply this statement, okay, then you may have issue because 20 is not divisible by 3. Okay, remember it's still subsampling, but it will reduce the number of feature maps. But it will maintain the size of the feature map. Okay, because we don't change the height and width. Okay, and we don't change the batch, but we change the number of feature maps in this batch. Okay, and if you want to include this statement, because this is TensorFlow low-level API, so if you want to include this statement with the Keras statement, then you need to wrap this with a lambda layer. Okay, so it's going to be something like this: Keras.layer.lambda, and inside here you provide, okay, this is the function, okay, that you want to call, okay, and then this will be properly included in a Keras model. Okay. The last one, okay, well, it's sort of a building blocks, sort of one building block in the CNN is called global average pooling. Okay, what is global average pooling? It is you can imagine it is one type of pooling, but it's going to pool the whole image, whatever the size is. Okay, it could be the original image could be as large as 100 by 100. It could be as small as like 10 by 10 or even 2 by 2. Okay, it's going to, well, it's called global average pooling, right? So it's going to take the whole image and do the average over all the values and output just one number. This is the meaning of the global average pooling layer. Okay, very simple, but it's basically like subsampling to the extreme, basically. Okay, so when do we use it? We use it, as you will see, okay, we normally, in the CN network, we normally stack up like a convolutional layer with pooling layers. At the end of this, pile, we have a max global average pooling to shrink each feature map into one number, and then we treat this whole array of feature map, well, as I said, because each one is now become one number, right? So we will treat this whole array of numbers, okay, as an input of the following layer, which will be fully connected layer, and then we do either the regression or classification task. Okay, as I will show you later. Okay, that's like the traditional CN architecture that we normally use. Okay, so the way to create a global average pooling is like this. Keras has its like default global average pooling. Okay, and because it's global average pooling, so you don't need to provide the size, because it's going to shrink every feature map, okay, into one number anyway, okay, regardless of the size. Okay, so it's equivalent to this simple lambda layer. Okay, basically this one is the equivalent to this one. So, but basically, I mean, obviously you don't need to use this. I mean, just use just call it global average pooling 2D. I mean, under Keras, you should be fine. Okay, so that's all the building blocks that you need to create a convolutional neural network. Okay, so how do we assemble them? Okay, as I said, like a CNN architecture, okay, normally we stack a few convolutional layers and followed by ReRU, okay, we will, we will have to have a activation function, right? As I said, like, I mean, for each value that you calculate from the previous layer, okay, by using the filters, okay, the filter basically help you to get like the weighted sum, right? And that value is going to eventually go through activation function. Normally we use ReRU, okay, it's not necessary ReRU, but a lot of time we use ReRU. Then the pooling layer, then another few convolutional layer and another pooling layer and so on. So this is like the image through this process, the image will get smaller and smaller. Okay, the reason image gets smaller and smaller may be contributed to by two factors. One is obviously the pooling layer, right? Because pooling layer is doing the subsampling. The other possibility is that, okay, you may have a large stride, okay, in the convolutional layer, which also help you to reduce your feature map size. Okay, so feature map size become smaller and smaller as it progresses through the network. But it also typically get deeper and deeper. Why? Because, okay, we are going to normally use more and more feature maps in the convolutional layer. Okay, because remember, each feature map basically represents different features, right? So the more feature map you use, okay, the more likely you are able to extract different features. Of course, we will also talk about like different some techniques that allows you to ensure the feature map, the feature that you extract by the feature maps will be as different as possible. Okay, we'll talk about that later. Okay, so anyway, so as I say, the CNN architecture normally will get, as it gets deeper, we will normally get more and more feature maps. Okay, and at the top of the stack, because each feature map will be shrink into one number, as I said, either using the global average pooling, or, well, it happened to shrink into one number already. Okay, and then you are going to stack, the feature map will, well, you can still call it feature map, perhaps, but it's going to become just one number stacking up, right? A lot of numbers stacking up. And you can sort of like consider it, like you can flatten it into one layer, right? And then, this will be followed by regular feed-forward neural network, which is like, normally it's a dense layer. Okay, we use a dense layer, okay, for the last couple of layers, okay, and then, do the prediction, either it's for classification, then we use the softmax, or if it's a regression, we use a different stuff. But basically, you get the idea. Yes.
那个 CNN 的网络，它会像就是一般的 dense 的 network 那样，就是可能叠几千层嘛，它的深度可能会到那样。
No. I mean, we normally only stack like a couple of, fully connected layers, not a lot. Okay. Remember, the fully connected layer, each fully connected layer, is going to create a lot of parameters, right? And one of the advantage of CNN over the MLP is that it doesn't have that many parameters. Remember, we talked about that when we compare the number of parameters. Remember, in the last lecture. But if you have too many fully connected layers, then the advantage of CNN diminish. So you normally don't do that. As I will show you later, okay, in some famous CNN architectures, okay, you will see usually we only have like maybe 2, 3 fully connected layer at the end. Okay, so anyway, let me show you the picture. So it's going to be something like this. So you have an input image. Okay, and why do we have multiple layers? Remember, okay, we have different channels for different color, right? For different RGB, right? I mean, so normally I mean, if it's color image, we have 3 channels. Okay, and then we have like a convolutional layer, which will create the number of feature maps. And if you use a pooling layer, the feature map gets smaller. But be careful, okay? Because the pooling layer, unless you use like a depth-wise pooling, okay, otherwise the number of feature map will be identical, okay? The number of feature map will be identical, okay? And then, okay, you can apply another convolutional layer with more feature maps that create more feature map. And then you apply pooling layer, you shrink, more, okay? And eventually, okay, either each one shrink into one number, or you can apply a global average pooling here to, to shrink each of these feature map into one number. Okay, so it will become just like the input layer of MLP. Okay, but and then followed by some dense layers. But as you will see in like some famous CNN architecture, we don't have a lot of these dense layers. And the last layer, well, it depends on what you want to do. You want to do the classification, you want to do prediction, regression. Okay, I mean, we have different, last layer, basically. Okay, so it's the typical CNN architecture looks something like this. Okay, the reason I say it's typical because as the research of CNN progresses, okay, there are more and more different architectures being developed, okay, as I will, tell you later, okay. So one common mistake, okay, is to use a large size of kernel, okay. For example, instead of using like a 5 by 5 kernel, okay, stack 2 layers with 3 by 3 kernels will be much better. So the idea is this, okay? Instead of using like a large kernel size, okay, using small kernel size but with more layers, more kernels is normally a better idea, okay? So you prefer more feature maps with smaller kernel size than a large kernel size with just a few feature maps, okay, or a few kernels, okay. With only exception, okay, with only exception is for the first convolutional layer. Okay, why do we say that? Okay. Because the first convolutional layer, okay, I mean, because here, when you apply the filter, okay, even if you use a larger filter, okay, you only have a limited number of input channels, right? There are only at most 3, okay, if you are talking about like RGB color image, right? But if you use like a large kernel size, say, somewhere here, then you are going to have a lot of, feature maps, right? As when you have more feature maps, if your kernel size is large, then the number of parameters grows very quickly, and it's not a good idea. So it's preferred that you use a smaller kernel size with more feature maps. Okay, but I mean, for the first layer, because we only have 3 like channels, so it's affordable to use like a larger kernel size. That's the only place you can consider using large kernel size. Okay, the other places you should avoid that, avoid doing that. Okay, so you can typically have a large kernel size for the first convolutional layer. I mean, in the later example, you can even see like not only 5 by 5 but also 7 by 7. Okay, I mean as large as like that. Okay, so usually we start of 2 or more. Okay, so this will reduce spatial dimension of the image without losing too much information. So large kernel size has its advantage, but if you use it for in the middle of the CNN, it is too costly. Okay, normally, so we don't do that. Okay, but using it for the first layer is possible. And since the input image only has 3 channels, so it will not be too costly, as I said. Okay, so this is an example. Okay, CNN architecture for the fashion MNIST. Remember the 28 by 28 image. Okay, we use all the time. Okay, for different network architectures. Okay, so here, okay, since we already learned the CNN, so we use it as an example. So you can see this. I mean, we use a sequential API to create this model. Okay, the first layer is a convolutional layer. Okay, so we create 64 like feature map, and we use a 7 by 7 kernel. Okay, so this kernel is a big kernel. Actually I should use huge kernel. Okay, because normally we don't use any kernel size larger than 5. Okay, so this is one exception. Actually, maybe just a little bit too big. Okay, but anyway, so activation is ReLU. Okay, padding is same. Okay, input shape is 28, 28, 1. So I don't think you have any problem with this and now. Okay, and then we immediately follow this statement immediately followed by a Maxpooling 2D. Okay, so we shrink the width and the height by 2, by a factor of 2, and then we apply 2 convolutional layer. Okay, with the same padding, still use ReLU, but you can see that because we already shrink the feature map by the width and height by 2, so we are affordable to have much more feature map. So the feature map number grows from 64 to 128, and we apply convolutional layer again. Okay. So we stack up these 2 convolutional layers and then apply a Maxpooling again to further shrink the width and height. And then we have another 2 convolutional layers, and this time we use the same padding, but we increase the feature map to 256. Okay, with kernel size 3. So normally 3 is the most common kernel size used in convolutional layer. Okay, it's not too small, it's not too big. Okay, you will see that. I mean, shortly. Okay, so anyway, okay, and after that, okay, and we apply another Maxpooling, okay, of size 2, and then okay, by now, okay, each feature map actually gets reduced exactly to 1 number. Okay. And we have, well, actually 256 numbers. Okay, so we use, flatten, okay, to make it 1 layer, 1 input layer. Okay, and then you can see we now create like a dense layer with 128 neuron with ReLU activation, and here is the important part. Remember I told you we will introduce dropout, right? We like to use dropout in the CNN, but we normally do not use dropout in the convolutional layer or pooling layer. Okay, we most likely use dropout in the CNN in the dense layers only. Okay, so use dropout here. We use and we another dense layer and drop out again, and the dropout value, I mean the rate can be as large as 0.50%. sometimes even higher. Okay, and then because remember this is a classification task with 10 classes, so the last layer is we have 10 neuron with the softmax activation function, and that's it. Okay, so this model, if you train it, okay, well, this is an explanation I think I already explained. So this model, okay, I mean, after you train it, it reached over 92% accuracy on the test set. So this is, remember, like, I mean, in the previous architecture, we didn't get such a high accuracy. We normally get like 89 something, okay? So this one is, 3% difference is huge, okay? Consider it's already very high, okay? So it's not state of the art, obviously, okay? But it's pretty good, okay, compared with the previous results. So clearly much better than what we achieved with dense network, okay, in the previous chapter, okay? So yeah, so now we are done with the basic elements of the CNN. Well, let's take 10 minutes break. When we come back, we are going to review a number of famous CNN architecture which can be considered in your project. Okay, so let's take 10 minutes break first. Thank you.